Hello everyone. This video is towards the fulfillment of deliverable 3.5 of the InnoDC project. The topic is on feasible implementable approaches to modeling dynamic converter interactions with large-scale AC system and wind farms. My name is Vaishally Bhardwaj and I would be presenting here on the feasible and implementable approaches for reliable AC-DC grid operation. My presentation is organized as follows. First, a short background on this topic is provided. In the next section, the implemented Preventive-Short-term-Corrective Security-Constrained Optimal Power Flow Model for hybrid AC-DC grid would be elaborated. Finally, some results are presented by applying the model for dynamic wind generation and load scenarios of large-scale AC-DC system. Reliable operation involves a sequence of decisions taken by the system operator under uncertainty. This uncertainty may be due to a lot of factors such as unplanned generation and load variations, as well as market factors. The current reliability management is based on the N-1 criterion. However, there are increasing system uncertainties. This is due to the increasing penetration of renewable energy sources, as well as the shift towards intraday markets. Thus, there is a need to move towards probabilistic reliability criteria. Out of the current approaches for reliability management, the preventive corrective security approach allows to take preventive as well as corrective actions. Thus, there is an opportunity for trade-off between the cost of measures taken and system risk. The flexibility from AC-DC converters by changing their active as well as reactive power set points can be utilized as a control action for reliable operation. This may be in the form of a preventive measure as well as a fast corrective action after the contingency owing to the smaller time constants of the converters. Such a control action is more economical than redispatch of the generator or load curtailment. Thus, there is a need to have a framework that captures the control actions of these devices with their respective time delays. In line with this motivation, a preventive short-term corrective security-constrained optimal power flow model for hybrid AC-DC system has been implemented. This is a steady-state optimization model that tries to emulate the decision-making for reliable operation by explicitly considering delays of the different control actions. The model also enables to evaluate the flexibility offered by the fast dynamics of the converters. This model is implemented based on the preventive corrective SCOPF model already presented in deliverable 3.3. In addition to the preventive and corrective stages, an intermediate short-term stage is added to capture the fast control response of the converters and the activation of frequency containment reserves or the automatic troop control from synchronous generators. The slower generator redispatch, converter redispatch, and load shedding is activated in the corrective stage. This model has been implemented by using the Julia jump platform. In this slide, we can visualize the optimization model of the preventive short-term corrective problem. It includes 4 different stages: the reference stage, preventive dispatch stage, and after the contingency, short-term stage and corrective stage. The reference stage is the starting point of the optimization problem, and it is the most optimal operational state of the system. The preventive dispatch stage signifies the implemented preventive control actions before a contingency. These control actions can be in the form of generator active power redispatch or converter AC side active power redispatch. The short-term stage signifies the activation of the droop response from generators as well as the fast control actions of converters. For our optimization problem, the decision variable for this stage is the converter AC side active power redispatch. The slower corrective stage follows in the end and involves the decision variables of generator active power redispatch, converter AC side active power redispatch, and the active power component of load shedding. The overall objective of the problem is to minimize the total risk, which is the sum of preventive actions cost, short-term risk, and corrective risk, where the short-term risk is the probability of the contingency times the cost of converter control actions taken in the short-term stage. The corrective risk is the probability of the contingency times the total cost of corrective actions from the generator, the load, and the converters. The constraints included for this optimization problem include the equality, inequality, and group constraints. The equality constraints include the AC grid and DC grid power flow equations, the nodal balance equations for AC and DC nodes, and the converter station power flow equations. The inequality constraints comprise of generator, load, and converter limits, the nodal voltage limits, and the branch thermal limits. The group constraints for the generators are implemented in the short-term stage. The total group response is based on the power lost during a contingency. The group constraints are relaxed to accommodate system losses and changes in power flow after a contingency. The individual generator group contribution is based on the rating of the generator. For the implementation of the preventive short-term corrective SCOPF model, an adaptation of the 67-bus AC HVDC overlay test system is considered. The system includes 34 synchronous generation units and 3 wind farms. There are 9 voltage source converters. The cost of corrective actions is 10 times than the cost for preventive actions for synchronous generators and wind farm generators. In total, there are 102 AC lines and 11 DC lines. For our analysis, there are 2 contingencies that have been considered. The first one is the contingency of generator 17 at bus 33 with a probability of 0.005. This is the largest dispatch generator in the reference stage. The second contingency is of generator 7 on bus 10 with the same probability. In this system, there are a total of 3 wind farms. Out of this, there are onshore wind farms at buses 2 and 5 and offshore wind farm at bus 67. Different wind scenarios are considered for these wind farms. This data is adapted from the hourly wind profiles of German onshore and offshore wind farms for the date of 17 January 2006 and simulated using the CoreRes software. Typical hourly load profile is considered for the system load, which is based on the hourly load trend for the same date for Germany. Each of these scenarios is solved using the preventive short-term corrective AC/DC SCOPF model. Here we can visualize the hourly profile for system load and wind generation. The left figure shows the trend of the system load and the total wind generation. In the right figure, the same trend for system load is seen, along with individual wind generation at the 3 wind farms. The preventive short-term corrective SCOPF model was run for each of the hourly scenarios, and the impact was assessed on the resulting preventive cost, short-term risk, and corrective risk. It is seen that the total risk changes with wind generation and system load. Higher risk as well as higher preventive actions cost is seen for the scenario with high load and moderate or low wind generation. For these scenarios, the resulting converter set points in the preventive stage were also observed. It can be seen here that the converter preventive stage set points also adapt based on the wind generation and system load scenario. Here we can see how the converter set point adapts for the different stages, that is the preventive, short-term, and corrective stages of contingency 1. These changes show that the set points are different for each of the different scenarios. Similarly, we can see the changes in the set points of the converter in the short-term and corrective stages for contingency 2. In this case, lesser changes are seen as compared to the previous contingency because of a smaller generator contingency in this case. An analysis was also carried out to evaluate the impact of considering converter actions in short-term stage. For this, the preventive short-term corrective AC/DC SCOPF model was run for some scenarios with and without the inclusion of converter set point changes in short-term. It was seen that without converter actions in the short-term stage, the total generator droop contribution constraint needed to be relaxed more. From the visualization, we can see that without converter actions in short-term, there is a slightly higher risk as well as preventive actions cost for each of the scenarios. Thus, I would like to conclude as follows. The post-contingency actions of AC/DC converters are faster as compared to other devices. Thus, a preventive short-term corrective AC/DC SCOPF model has been implemented, which captures this temporal aspect of the different control actions in reliable operation. Here, the fast response from converters and the activation of frequency containment reserves is modeled in the post-contingency short-term stage. This model was implemented for the 67-bus test system, and different hourly wind generation scenarios and system load was applied. It was seen that there is higher risk as well as preventive actions cost for the scenario with high load and moderate or low wind generation. It was also seen that without converter actions in the short-term stage, there is a higher risk and preventive actions cost. This highlights the flexibility offered by the fast converter response in reliable operation. These are some of the references that have been used to carry out the above analysis. With this, I would like to end my presentation and thank you for tuning in.